everybody, and welcome back for Unit 6, Lesson 3, which is all about interpreting the meaning of an integral, as well as determining whether your estimate is an over or underestimate. So now that we know how to find integrals, we're going to be going a little bit deeper into what these things actually mean. The first learning target for today is I can interpret, which means determine the meaning of the areas associated with the graph of a rate of change function as the accumulation of change in the function, so the accumulated change, using correct units. The second learning target for today is going to be I can determine whether an approximation, so we've been learning how to approximate using the Riemann sum approximation methods as well as the trapezoidal method. We're going to determine whether an approximation is an underestimate or an overestimate for the value of a definite integral. So now that we know it's an estimate, is it too big or too small? Let's start by talking about interpreting. Just like when we learned how to interpret derivatives, we said a derivative is telling you the rate of change of a function at a specific moment in time. We need to know how to interpret the integral using correct units. When we learned how to interpret a derivative, we said there were three pieces to the interpretation. There's the noun, so what is it actually finding? There's the units, so what are the units of measurement? And then there's the time. So noun, units, and then time. And we said the abbreviation here is NUT. It's all in a nutshell. So how do you interpret in a nutshell? You use the noun, the units, and the time. When we compute the value of an integral of a rate of change function, we are computing the change in the quantity that's being measured. So if you compute the integral of the rate of change of the amount of water in a bathtub, you're finding how much the water in the bathtub has changed by. So you're actually finding what was the change in the function. The units you're going to use are going to be, you can figure these out by using an integral by multiplying the output units by the input units. This comes from the fact that we're finding the area. So anytime you find an area of a rectangle and you're doing base times height, you're going to be multiplying the output units times the input units. Base is the input units, height is the output units. So when you find these areas, your units are going to be the input times the output units. Last but not least, the time. When we specify the time, when we calculate an integral, we're going to use the bounds of the integral, the lower and the upper bounds, to describe the interval or the section of the graph that we're looking at, the interval over which we're finding that change. So let's practice this. Suppose that T of x gives the rate of change of the temperature of a cup of coffee, measured in degrees Celsius per minute, and x is measured in minutes after it's poured. Suppose that you calculate the integral from 0 to 12, and you get negative 25. Using correct units, interpret the meaning in the context of the problem. So let's start by making sure we read the important information in the question. First, we know that T of x gives the rate of change of the temperature of a cup of coffee. That means that when we find the integral, we're figuring out the change in the temperature of the cup. It's not the rate of change, which is what we have, is how fast it's changing. When we integrate, we're figuring out how much did it change by. So did the temperature go up or did the temperature go down? Now, the units of the function that we have are degrees Celsius per minute, and x is the minutes after it's poured. So to figure out the units for our integral, we're going to have to multiply degrees Celsius per minute times minutes. And then last but not least, the bounds are going to tell us the interval. So the bounds here, the lower number is 0 and the upper number is 12. That means that it has been from 0 to 12 minutes after it is poured, because the bounds are always x values. So what we're going to do now is put this all together to make a sentence. So we're going to say the integral from 0 to 12 of t of x dx equals negative 25 gives this is the noun part. If we're started with the rate of change, so how fast the temperature of the cup of coffee is changing, then when we integrate, we're finding the change in the temperature of the coffee. Now, that's like the noun. The units are going to be degrees Celsius per minute times minutes. Now, in this case, because you're dividing by minutes and multiplying by minutes, the minutes cancel, so it's just degrees Celsius. So it's going to be measured in degrees Celsius, which makes sense. If I'm figuring out how much did the temperature change by, it's going to be it went up by this many degrees Celsius or down by this many degrees Celsius. And then I need my time. And so I would say from 0 to 12 minutes after the cup was poured. Now, the second part of this interpretation is saying specifically, what does this negative 25 tell you? So you would say, since the integral from 0 to 12 of t of x dx is equal to negative 25, the temperature decreased by 25 degrees Celsius from 0 to 12 minutes. Now, I'm using the word decreased here because this is a negative value. So here's what it means, and then here's specifically what the 25 tells me is that it went down by 25 degrees Celsius from 0 to 12 minutes. Now let's talk about the next example. It says, suppose v of t represents the velocity of a car traveling on the highway measured in meters per second after t seconds. Using correct units, interpret the meaning of the integral of your velocity function from 0 to 12 is equal to 30 in the context of the problem. The first thing we need to make sure we know is what velocity means. So we know that v of t represents the velocity of a car traveling on the highway. The units are meters per second after t seconds, and my bounds, which is my time interval, are from 0 to 12. One thing that's really important to note here is that velocity is the rate of change, so it's the how fast of position. It's the rate of change of position. So that means that when we find the integral of velocity, we are finding the change in position. So we would say that the integral from 0 to 12 of v of t dt gives the change in position. And for those of you who have maybe had some experience with physics, you'll know that we often call that the displacement of the car. Now my units are going to be meters per second times seconds, which means it's just going to be meters. So I would say measured in meters which makes sense. If you're figuring out the change in a position, you wouldn't ever say it's like 10 meters per second away from where it started. It's going to be 10 meters away from where it started. And then you would say from 0 to 12 seconds. Now, the second part of interpreting is saying specifically what does the 30 tell you? So you would say since the integral from 0 to 12 of v of t dt is equal to 30, the car is 30 meters away from where it started after 12 seconds. Okay, now that we've kind of practiced interpreting the meaning of an integral as the change in whatever happened. So if it's the rate of change of position, you get the change in position. If it's the rate of change of the temperature, you get the change in the temperature. If it's the rate of change of the water, you get the change in the amount of water that you had. The other part of this is to determine the accuracy of a Riemann sum. So when we use a Riemann sum, we know we're getting an estimate, but how do we know if it's an over or an underestimate? Sometimes we can determine whether our estimate is an over or underestimate using features of the function. But when we're asked to do this, it is always best to draw a picture in order to answer the question. Do not try to just memorize all of this. Drawing a picture is really the best strategy for figuring this out. So let's talk about right Riemann sums first. First, when you have a right Riemann sum, I want you to look at whether the function is increasing or decreasing. Now, this information is usually going to be in the instructions. You need to make sure you read the instructions really carefully because it's going to tell you whether your function is increasing or decreasing. If you have an increasing function and you use a right Riemann sum, here's how you can draw a picture. Start by drawing a picture like the one you see here, which is an increasing function. Then I want you to make one big rectangle. So here's the left and here's the right, and use the right side to make the height. You will notice that this rectangle is too big for the graph that you're looking at. So if you're using a right Riemann sum and your function is increasing, you have an overestimate. Now, what if you have a decreasing function? Well, same strategy. So draw a decreasing graph. It's literally just a graph that goes downhill. Make one big rectangle so you have a beginning and an end, and use the right side to make the rectangle. Once again, you're going to see we have one big rectangle, but this time it's too small. So we would say that we have an underestimate. Next, let's look at whether we are an over or underestimate using a left Riemann sum. So again, we're going to look for whether the function is increasing or decreasing. And again, this information is usually in the instructions, so make sure you read the directions. If you have an increasing function, so literally just start by drawing an uphill line, and you make a rectangle, and you use the left side to make the rectangle, this rectangle is going to be too small. So then it's going to be an underestimate. And if you take a decreasing function and you make one big rectangle and you use the left side to make the height, you're going to get an area that's way too big. So that's going to be an overestimate. And it really comes down to what kind of graph do you have? Is it increasing or decreasing? And what kind of estimate are you using, left or right? So you need to look at both of those things in order to make this determination, and drawing a picture is the best way to do it. Now, the last thing is, what if you have a trapezoidal sum? So we're never going to ask you if a midpoint is an over or underestimate because you can't really determine that just based on features of the function, since it's going to be a little bit too big sometimes and a little bit too small sometimes. For a trapezoid, though, we can make this determination, but rather than looking at whether the function is increasing or decreasing, we need to look at whether the function is concave up or concave down. And again, this information is usually in the instructions. So you got to read the directions. If you have a concave up function and you make a trapezoidal sum and you make one big trapezoid, you're going to get an estimate that is too big. So you would say that this is an overestimate. And if you have a concave down function and you make a trapezoidal estimation, you're going to get an estimate that is too small. So you're going to have an underestimate. Underestimate. I totally spelled that wrong. UNDER estimate. Okay, let's see this in action. So problem number 3 here says you may use a calculator. So I've got my calculator out. Water is being removed from a tank modeled at a rate modeled by R of t liters per hour, where R is differentiable and decreasing on 0 to 8. Selected values of R of t are shown. Use a left Riemann sum with the 4 subintervals indicated by the table to estimate the total amount of water removed from the tank during the 8 hours. Is this an overestimate or an underestimate of the total amount of water removed? Give a reason for your answer. So there are 2 parts to this problem. Part number 1 is use a left Riemann sum with 4 subintervals to estimate the total amount of water removed. So if R of t is telling me the rate at which water is being removed, then the integral is going to tell me how much water was removed during the 8 hours. Now we want 4 subintervals. So subinterval number 1 is going to go from 0 to 1, then from 1 to 3, then from 3 to 6, and then from 6 to 8. So in order to organize my work here, I'm going to draw 4 little lines. And I'm going to have 0 to 1, 1 to 3, 3 to 6, and 6 to 8. Now I want to use a left Riemann sum. So I'm going to draw the heights of those rectangles on the left side. For the 0, my height is going to be 1340. And then I'm going to have 1190. And then I'm going to have 950. And then I'm going to have 740. And so in order to calculate my integral, the integral from 0 to 8 of R of t dt, I would do the base, which is 1, times the height, which is 1340, plus the base, which is 2, from 1 to 3 is 2 spaces, times the height, which is 1190, plus the base, which is 3, times the height, which is 950, plus the base, which is 2, times the height, which is 740. Now, it is very, very important that you actually write all of that out the way that I'm showing you. You want to kind of set up your work first and then show that the integral would be equal to these calculations. Oftentimes on the AP test, and I believe this is an example of that, this was actually a non-calculator question on the AP test. Now that means that it could be very easy to make an arithmetic error, but by showing this setup that you know that the integral can be calculated by doing base times height these 4 times, you're going to get partial credit or most of the credit just for showing that setup, even if your final answer is wrong. So it's really important that you kind of organize your work however works best for you and then show that the integral is equal to these calculations. So on my calculator, I'm going to type in 1340 plus 2 times 1190 plus 3 times 950 plus 2 times 740, and I'm going to get 8050. Now in this case, the units would be, if you do liters per hour times hours, it would just be liters. So now we know that 8,050 liters approximately were removed from the tank during the 8 hours. In order to determine if this is an over or an underestimate, we need to think about the type of Riemann sum that was used, in this case, a left one, as well as whether this is an increasing or decreasing function. If I go back to the original problem, it says that r is decreasing. So I have a function that is decreasing. So in order to visualize this on my paper, I'm going to draw a decreasing function. And now I'm going to imagine making a left Riemann sum. So a left side sum would mean using this rectangle, which is going to be too big. So I would say the estimate is an overestimate. That's the first thing I need to say. Is it an over or an underestimate? Because, and now there are two components to my reason. The reason that this is an overestimate is I used a left Riemann sum, but also because the original function was decreasing. If you go back to what we talked about on the previous page, if we used a left Riemann sum, but the function had been increasing, we wouldn't have gotten overestimate. We would have gotten that this was an underestimate. So there are two components to my reason here. So I would say because a left Riemann sum was used, so that's the first part, and r of t is decreasing. So it's a combination of the fact that we used LRAM and the fact that the function was decreasing that gives me that this is an overestimate. That's why we need to make sure we say both of those pieces of the reasoning in our explanation. For number 4, again, we're going to use a calculator. So we've got the same table, but this time we're going to use a right Riemann sum with 4 subintervals and then determine whether that is an overestimate or an underestimate. So in order to organize my thinking here, I like to start, this is how I visualize it. I have the intervals from 0 to 1, 1 to 3, 3 to 6, and then 6 to 8. But this time I'm going to use the right side of each interval as my height. So in this case, it would be 1190, and then 950, and then 740, and then 700. Now, I'm going to show that I understand how to compute this integral. That's really important. So the integral from 0 to 8, r of t dt would be equal to 1 times 1190 plus 2 times 950 plus 3 times 740 plus 2 times 700. Now I'm going to use my calculator to actually perform the computations. Again, on the AP test, I believe this was actually a no calculator question, so that's why I think showing your work is so important here. You can still get partial credit even if your final answer was wrong. And I got 6710. And this is going to be liters because if you multiply liters per hour times hours, you're going to get liters. And now we need to say whether this is an over or underestimate. Now, again, this was a decreasing function. It told us that in the instructions. So off to the side, I'm just going to sketch a little picture of a decreasing function. And I'm going to use the right side to make a rectangle. And I'm going to see that that's too small. So I would say the estimate is an underestimate. That's the first part of my answer. Is it over or is it under? Because, and now there are two components to my reasoning. It's because a right Riemann sum was used, and also r of t is decreasing. If we had an increasing function, this would be a totally different story. All right, that is the end of our video for today. Thank you guys so much for watching, and I'll see you soon for some practice.